Welcome back, everyone. Trust you had a deserving break. Just then, to recap, this topic is about looking at the dense medium cyclone and why the simple device is sometimes unpredictable. And we will continue now with the second half of this presentation. So we have looked in the first session at the cyclone design. All characteristics is all relating to optimal performance of the dense medium cyclone. Now we move on to medium characteristics. So when we look at medium characteristics, we have to first look at hydrocyclones. Maybe a bit of a surprising comment, but let's just think about hydrocyclones. It utilizes water as a transport medium that will transport the solids. It separates on size, and if you want to make a change to the cut size on the hydrocyclone, you make some certain modifications with the cyclone configuration and the feed conditions to the unit. The dense medium cyclone utilizes magnetite or ferrosilicon as a transport medium. It separates on density, and then the changes in the cut point or the cut density is done by changing the medium feed density outside the dense medium cyclone. So why now this comparison? Well, if you have a dense medium cyclone and you're processing ore and you stop the ore, but you only process the medium through the dense medium cyclone, you don't have a dense medium cyclone anymore. You have a hydrocyclone. Because let's rethink. What is the definition for the classification? It needs water and solids. And the medium is a mixture of water and solids. So when we are making then changes to the cyclone configuration, we inadvertently also impose a change on the cut size of the medium inside the dense medium cyclone. So that's why on dense medium cyclones, we don't normally change the cone angles or spigots unnecessarily. The dense medium on the hydrocyclone, you've got then more water reporting to the overflow and more solids reporting to the underflow. That gives rise then to a difference in density between the overflow and underflow of the hydrocyclone. And the same applies to the dense medium cyclone. You've got a feed density coming in, and then you've got a lower overflow density and a higher underflow density. About 1/3 from the bottom of the cyclone, that's where the cut density is generated. So the feed density is the operating density. In some cases, operational people think that that is the cut density. It's not the case. It's slightly higher than the operating density. So this formation of different densities between the overflow and underflow of a dense medium cyclone is very important for us as suppliers to determine the behavior or performance of the dense medium cyclone. If the medium is too coarse, or you're operating at a too low density, you've got medium that is settling out very quickly. And its impact on a dense medium cyclone is that you've got predominantly most of the medium reporting to the underflow, and then mostly water and maybe a small amount of medium reporting to the overflow. You've got therefore a very large difference between the overflow and underflow densities, and we define that then that the medium is unstable. So to illustrate that then on a different scale, let's look on the density profiles on a radial format within the dense medium cyclone. The red dotted line is referred to as the locus of zero vertical velocity. Flow patterns inside that radius moves to the inside and out to the vortex finder, and material on the outside moves downwards towards the spigot. So when we introduce then a particle of a density of 1.9, it migrates to the right density range. And the lighter density particle will migrate to its own density range, which sits within the area of the locus of zero vertical velocity and will report to the overflow. When the medium is unstable, you will see the density profiles has now changed on these circular areas. Now we've got the same high density particle reporting to the outside, but now the lower density particle is also reporting to the outside of the locus of zero vertical velocity radius, and it's reporting then to the underflow. So this is just an illustration on the impact that an unstable medium will have. But you can also have the medium that is too fine, or you're operating at a too high operating density for that medium, and then the medium does not really want to separate, and that refers to the medium being too viscous. You've got then too close a density difference between the overflow and the underflow of the dense medium cyclone, which can also impact on the separation efficiency. This difference in densities we use then to calculate differentials. So in this example, we've got the various densities, we've got the cut density. So the differentials that we can look at is the feed to cut density cut point, which we refer often as the offset, feed to overflow differential, which should range between 3% and 12%, and then the underflow to overflow differential. That is just subtracting the overflow density from the underflow density, or vice versa, underflow density from overflow density. And if the answer is between 0.2 and 0.5, you are within specification. The feed to overflow calculation is the one that we mostly use. And the reason for that is that access to the spigot area is often not possible. Either it's too difficult to get to that area, or you're not allowed in that area. For example, in a diamond processing plant. So the feed to overflow differential, the formula is given in the bottom block, bottom right-hand block, and it just illustrates then how this calculation is performed. And if the answer is then between 3% and 12%, the medium is deemed to separate acceptably within the dense medium cyclone. If we are below 3%, we are going into a viscosity region, and if we're above 12%, we're going into an instability region. There's also graphs available instead of doing the calculation, and the 3 to 12% range are given by this green shaded area. This graph, we're looking at the cyclone overflow density on the y-axis, and we use the circulating medium density on the x-axis, and we just combine then the 2 points. Outside areas are then illustrated for high viscosity or low viscosity areas. And once you've got the two densities, you just connect a point and you see in which area the intersection takes place. That gives the indication of what is happening with the medium inside the dense medium cyclone. That's a very important reference point for us as suppliers to start investigating if there's a strange behavior within the dense medium cyclone. So some possible reasons that can impact then on the on different differentials being formed outside the specifications could be the medium quality, the medium size distribution, the grade of the medium, the impact of residual magnetism or non-magnetics that's building up in the medium stream. Magnetite and ferrosilicon has got different grades that's available for processes, and they normally specific to certain specific gravity medium densities that you are planning to use on your process. There are also other grades available other than these on these tables. And if you use the wrong grade, what can happen then is that the cyclone efficiency can be compromised, and it can also affect the differentials on the dense medium cyclone. So it's important when you are using a specific grade of medium to just check with the supplier if that is the correct grade for your operation. In dense medium cyclones, when you want to reduce the cut density, you reduce the operating density. So the operating density on this graph is on the x-axis, and you get to a point where after, if you reduce the cut density even more, or the operating medium density even more, that the cut density starts to increase again. So this is a very unexpected behavior that one can observe on a dense medium cyclone. And this is the area where instability is starting to come into the equation. So people that is not familiar with this type of behavior will try to reduce operating density further and further to reduce the cut density. And then the opposite starts to happen. We have looked now at the density profile in a radial format on the dense medium cyclone, and we've also seen that there are a density profile on the axial axis of the dense medium cyclone. So what I did was I was trying to combine the two density profiles, and there's just an illustration of what density profiles I've looked at, and you get to a graph that looks, or a picture that looks like this. And that represents then, on a basic level, the density band that we are looking inside the dense medium cyclone. There is the actual CFD picture on the right-hand side, slightly different from my attempt, but it's just illustrating that there are different density bands within the dense medium cyclone. And if we start to impact on the behavior of the medium characteristics or the medium performance, then it will have an impact on the performance of the dense medium cyclone. So we've looked now at cyclone design, all characteristics, medium characteristics. So now we move on to the plant operation. For optimal performance of a dense medium cyclone, we need to have adequate retention time. That relates to the cyclone design. We need to operate at the correct cut density. It's no use having a very efficient dense medium cyclone, but it's not operating at the correct cut density. And that is where the medium characteristics that we've just discussed is coming in. Now we also need to have then the correct operating conditions. And the combination of these three factors gives you then the best operating conditions for a dense medium cyclone. Coming back then to the process flow diagram. I'm going to discuss each of these items separately, just to illustrate what impact it can have on the performance of the cyclone, or what aspects one just need to take note of. So if we look at the screening on the feed preparation screen, the purpose on the feed preparation screen is to remove fines from the process. But if we start to impact on the feed rate, we increase the feed rate, we affect the screening efficiency. And also we are introducing more water into the medium circuit via the more surface area that's been produced, or due to the larger amount of particles flowing into the dense medium circuit. That water enters the point after the density has been monitored by the densitometer. So this can lead to problems in terms of obtaining the correct cut density. Panel wear can impact on the mass split in your process. You can send material that should have gone to the dense medium cyclone into the fines fraction, and it may be a process that's not as efficient as a dense medium separation. Therefore, your yield is not maximized. Spray water, inadequate spray water can impact on the screening efficiency. Pegging and blinding, also impacting on water carryover and screening efficiency. And then the actual screen operation, the actual mechanical operation, can also impact on the performance of the feed preparation screen. On the drain and rinse screen, main purpose is to drain the medium. So if there's too much medium being carried over, or the screen panels, the screen is not operating efficiently, or the screen panels is pegged or blinded, then you have got more carryover of medium to the rinse section. And that medium has been washed off and it goes to the magnetic separator. And one can then overload the magnetic separator. Panel wear. As the panel starts to wear, we are introducing more non-magnetics into the medium circuit. That can impact on the flow patterns within the dense medium cyclone. The slurry characteristics of the medium. The spray water. We don't have, if we have inadequate spray water, we just contribute to the medium losses. The pegging and blinding, I've talked about the drainage. And then panel apertures between the desliming and the drain and the rinse screen. Now, the standard industry, or the industry standard, is that you've got larger panels on your feed preparation screen and larger apertures on your feed preparation screen and smaller apertures on your drain and rinse screen. You do have the situation sometimes where operations will have the same apertures on both screens. And as the apertures then increase on the drain and rinse screens due to wear, we then have material that's starting to build up in the medium circuit. On the odd occasion, you can have situations where panels with larger apertures are actually being installed on the drain and rinse screen. Maybe sometimes just because of a shortage of stock, of not understanding the impact on the process. That situation can then lead up to buildup of non-magnetic material in the medium, and that impacts on the separation efficiency of the dense medium cyclone. On the dense medium cyclone, feed rate is important. That impacts on the medium to ore ratio and the separation efficiency. We talked about the residence time. The operational head of the unit, very important because it impacts on the capacity, the medium to ore ratio, and the separation efficiency. We've talked about the differentials. We just need access to obtain those densities. The product yield, if that changes significantly, it can impact on the spigot capacity and then the separation efficiency. As the feed size distribution changes, we've seen that there is a optimal limit for each dense medium cyclone diameter. It can impact on the separation efficiency, possibly on the cut density shift, and then block features if the particles are too big. When you've got multiple dense medium cyclones, the distribution between the two cyclones or the three cyclones can also impact on the efficiency of the dense medium process, because there could be bias distribution between these cyclones. So one has to take note of how you distribute the feed between the multiple units. Maintenance and inspection accesses. If you can't get into the cyclone to inspect it, it can lead to unplanned stoppages because of failures that's happened within the cyclone. It also impacts on the separation efficiency. Incorrect medium grade, we talked about impacting on the differentials. And then you can have incorrect parts that is then fitted to the dense medium cyclone, leading to misalignments, and that can lead to particle misplacement. And then incorrect installation or too small collection boxes. It sounds strange, but it has happened in the past where the boxes are not capable of draining away the float and the sinks volumetric flow streams. And then that just starts to build up and push back into the cyclone, and that impacts then on the separation efficiency. On the circulating medium, some fluctuating sump levels can impact on the operating head of the dense medium cyclone. The cyclone is pump fed. If you have a manual pump, this is a VSD, variable speed pump. On the manual pump, the operating head is normally selected to be slightly higher so that it compensates for the wear on the pump impeller. So as the pump impeller wears, the operating head will drop until it reaches then our minimum recommended limit. On the VSD, you can speed up the pump to maintain the correct operating head continuously. Sump level versus the net positive suction head on the pump. There are situations that I've seen where the sump levels fluctuate or are too low and the pump is not efficient, and that impacts then on the volumetric flow that can be pumped to the dense medium cyclone. On the dilute medium sumps, the sump level fluctuations here would impact on the magnetic separator performance. And then the same applies with the sump level at the net positive suction head. If the pump is not operating efficiently, it's starting to impact processes after the pump. So make sure that those are consistent operating units. On the magnetic separator section, and I believe there's going to be another section on magnetic separation in this workshop. But briefly, looking at the operating level, magnet position, the gap between the drum and the discharge lip, height of the drum, magnetic loading, and volumetric capacity. These are all factors that influence the performance on a magnetic separator. And one should not underestimate what impact the magnetic separator can have on the process. Then on to densifiers. Now, the primary activity of the densifier is to remove water from the correct medium circuit. A secondary activity can also be partial cleaning of the medium, because you are processing medium with non-magnetics, and in most cases that non-magnetics has got densities lower than the medium density, so you get a particle dense medium separation taking place as well. Obviously depends where the densifier is installed, on which leg. So there are basically three criteria, or three locations we would use the densifier. However, the first one, the correct medium bleed, showed by the arrow, is not a densification process, or it is a densification process, but you don't use a specific item. You just divert more medium to the dilute circuit, and the magnetic separator will then clean the medium and remove the water. The correct medium bleed is sometimes inconsistent, and that also influences the performance of the magnetic separator. Then you can have a densification activity on the dilute medium circuit, or you can have a densification activity on the correct medium densification. Most of the densification circuits are on the correct medium circuit. Not all operations require densifiers. If your operating density or your cut density is low enough and there's not too much water entering your process, then the magnetic separator will be adequate and no need for densification. But you do have applications like ultra-high density separation, where you may require more than one densification stage to reach the density that the process desires. So looking at the densifier, inconsistent operation can influence then the overflow or the overdense densities, blockages, incorrect operation, incorrect number of operating units, incorrect parts, or no operation. This all relates to have the densifier operating as consistently as possible. So these factors that I've just mentioned, they can impact on the behavior of the densifier, leading to inconsistent operation, and that just leads to instabilities within the process. There are basically two types of densifiers that we use. We've got a pipe densifier where it's got a low water removal rate, but you will also see it's a lower medium losses that's associated with the pipe densifier. The cyclone densifier has got a higher removal water rate, but you will also have higher medium losses. So how this now happens is that the overflow where the water is now removed from needs to go to the dilute medium circuit, and it will then move to the magnetic separator. But the magnetic separator is not 100% efficient. So whatever medium moves to the dilute medium circuit and to the magnetic separator, a portion is going to be lost. So the pipe densifier has got a lower water removal rate. In other words, a high portion of the incoming volume reports to the underflow and back to the correct medium tank. It's done so for a specific reason, but if you want to increase the water removal rate, you need to pump more medium to the pipe densifier. The cyclone densifier do not require such a high volume of medium to be pumped to the unit because it's got a higher water removal rate. But just take note that the higher medium losses may occur then using the cyclone densifier. So the cyclone densifier is predominantly used on magnetite circuits, which is coal, and the pipe densifier predominantly used on ferrosilicon circuits, which is other than coal. On two-stage densification, it's a combination of the pipe densifier and the cyclone densifier. So we've talked about cyclone design, all characteristics, medium characteristics, and the plant operation. So moving on then to sampling. If you sample the incoming feed and the outgoing products, you have a holistic performance of the process, and you have an indication of what's the quality that's being produced from the separation process. If you want to look at the efficiency of the dense medium cyclone, we need to sample the feed, overflow, and underflow streams. That will give us an indication of the performance of the cyclone. Just to take note on this topic, or this on this section, that sampling frequency or the sampling period, the time period, needs to be as short as possible. If you do your evaluation around the dense medium cyclone over a long period and there's fluctuations within the process, you may get a distorted picture and you're not sampling the cyclone efficiency anymore, you're sampling the process efficiency. Then there's also metallurgical checks, circulating medium sump or feed line, the densifier overflow and underflow streams, the magnetic separator overdense streams, as well as then the feed to the magnetic separator and the effluent streams. Those are just sampling points where checks can be conducted to ensure that the process is operating as efficiently as possible. When we are doing sampling of the solid ore entering the plant and exiting the plant, make sure that you use a correct designed sampling device. You do get applications where people would use a shovel, believe it or not. The problem with this is that it introduces bias. And when there's a problem with the dense medium cyclone, we as the suppliers require data. But if that data is biased, then it means nothing to us, and we cannot come up with the correct answer. When we look at the efficiency in the dense medium cyclone, we can obtain samples around the cyclone, or we can use density traces. That is available these days. You have your standard density traces of various densities, various sizes that you will introduce into the cyclone, and you will collect it manually afterwards. You also have magnetic density traces that can be collected via magnets. And then you've got radio traces. Radio traces gives you instantaneous indication of what the separation curve looks like inside the dense medium cyclone. They are becoming more and more popular. And then you still need to sample slurry streams. Now, we're all familiar with the Marcy scale and the Marcy Bekker, but make sure when you're sampling the slurry streams that the Marcy scale is calibrated and it's operating correctly. Also, sampling via the Marcy Bekker, make sure you take the sample correctly. Because if you take incorrect density samples, it may have an influence eventually on the dense medium cyclone. For example, if you have to calibrate the densitometer to the medium stream, if you sample incorrectly, you are calibrating the densitometer incorrectly. So that's on sampling. Moving to maintenance. If you do no maintenance, then it costs a lot of money to correct the problems that is generated inside the process. You can also do too much maintenance, which is also not optimal from a monetary point of view. So there's an optimum zone where you need to have some preventative maintenance being conducted to reduce, or corrective maintenance being conducted to reduce then the impact of money spent on maintaining the unit correctly. So the guidelines given by the suppliers, do not underestimate that or do not ignore it, because every cyclone do experience wear. Normally, most of the wear takes place about 1/3 from the bottom of the cyclone, as that is where the dense particles might accumulate. And one needs to make time to inspect the unit to see if there's a problem inside the unit. You can see on the picture on the top right-hand side, that cyclone have been patched on the outside. The problem is when you look internally, this is a ceramic line cyclone, there's no more tiles on the inside. The picture on the bottom left-hand side is also an illustration where a ceramic lined unit had been used and where foreign steel has entered the unit. The unit didn't leak, but as you can see internally, there's no smooth surfaces anymore. So that led to inefficiencies as well. So in both these examples, we are distorting or affecting the internal wear surface, leading to a high probability of turbulence and then misplacement of material. Alternative material of construction are available to address these type of situations. The material characteristics that's been processed, if that changed, that impacts on the wear as well. The pictures on the right-hand side, top and bottom, belong to each other. The cone and the spigot section, you can see the impact of high wear on the unit. Process conditions, where the yield has changed or the top size has changed, also impact on the material, on the wear rate. And then operating conditions, where the operating head has increased or the solid throughput has increased, will impact on the performance of the cycle. You will see on the bottom left and middle picture, Also, that the vortex finder can be exposed to high wear. That is where high yields to the overflow is applicable. So being able to inspect the cyclone is of paramount importance. That will just prevent unplanned failures. You often see the spigots being run to destruction, and suppliers will give then an indication that, hang on, there needs to be a certain ratio between the spigot and vortex finder. That's the graph that Multotec has produced. They will see that the efficiency, which is the red line, runs pretty constant at 0.012 efficiency, up to about 0.8 to 0.85, which is on the bottom x-axis. Ratio of spigot to vortex finder diameter. Often, the reason for this guidance from the suppliers is not well understood, and it's ignored, and then the spigot is run till destruction. So why is the spigot to vortex finder ratio so important? This picture illustrates where a spigot diameter and vortex finder diameter was exactly the same. As you can see, at the entry point of the vortex finder, there's a lot of turbulence, and it seems that the vortex finder wants to collapse. The question is, how is the float material getting into the overflow stream? And sometimes people would say via the air core. Well, that is unfortunately not correct. The center picture illustrates the air core in a cyclone, and as you can see straight through the cyclone. So it cannot accommodate material transport. So the material that's leaving to the overflow leaves in the stream that is between the inside of the vortex finder diameter and the outside of the air core. So if we increase the spigot diameter, we're increasing the air core diameter, and that starts to reduce the transport capability floats material through the vortex finder, and that leads to inefficiencies. Next, some quick checks. The density medium cyclone is part of a process. So if you want to optimize the unit, we can't just focus on the cyclone alone. So some guidelines measure the differentials, but you need to have access sampling points. That gives you an indication of the medium, as discussed earlier. Check the magnetic separator efficiency. Just check on the medium losses. Your spray nozzle operation on the screens. Make sure it's optimal. It's operating optimal. Reduces the medium losses. Check your medium quality and the size distributions, amount of non-magnetics. You can check for misplaced material as a quick reference. Ensure the correct operating head on your dense medium cyclone and understand what impact the operating head has on the operation of the unit. Higher operating pressures can increase the differentials across a dense medium cyclone, so one should not underestimate what high operating pressure can do over and above increase in wear rate. But there are situations sometimes where high operating head did prove to be beneficial. And if a densifier is used, make sure that its purpose is understood so that people can pay attention and look after the unit. So some comments. When you're looking at pre-concentration of valuable stones, 100% recovery is required. So the selection of the unit needs to be spot on. Pre-concentration of minerals, where you want to remove then maximum waste and minimum product loss, we need to know what is the material or the densimetric profile so we can ensure we select the correct dense medium cyclone. On bulk commodities, you're looking at maximum recovery to produce the correct product quality. So depending on what application a dense medium cyclone is used, it may have a slight different approach in terms of the cyclone selection. If you've got a fine fraction, which is a significant portion, and it can have a large potential revenue, and the cut density or the densimetric profile indicate that this portion can be maximized by operating at a different cut density, then it may be worthwhile consider splitting the dense medium circuit into a coarse and a fine section. It does increase the complexity of the dense medium process, but it may benefit the potential revenue that you can get from the process. If the densometric profile is very similar and it's still a large portion of fines, and let me just rephrase. If the fines is a large portion and it can contain a significant portion of revenue, maybe consider using a two-stage DMS process. That is just to beneficiate or ensure that optimal separation efficiencies or the efficiency of the process can be maximized. It's not always common, but that's an option that can be exploited. Then with all these discussions, I decided to just have a look at ChatGPT. And the question posed to ChatGPT is how to optimize a dense medium cyclone. This I've done because I realized that a lot of people tend to refer these days to artificial intelligence to get guidance. So I wanted to just compare what artificial intelligence is saying with regards to this topic. So the first item that came up was particle size analysis, and the sentences was as I obtained it from the internet. So it indicates that it does play a role, which is a fair statement. It indicates that it's crucial for selecting the appropriate cyclone size and the operating conditions. So I can accept that comment, but we realize that also if there's a lot of fine material, we can have certain operating conditions modified around the dense medium cyclone to just accommodate finer fractions that shouldn't have been there. Cyclone geometry, it indicates that we need to look at the diameter, the cone angle, vortex failure diameter, and spigot size. It says adjusting these parameters can affect the separation efficiency. Well, that is not completely true. We do select the cyclone up front based on the mass balance, but we don't change the cone angle. The vortex failure diameter is only changed whenever there is a requirement in terms of spigot loading. So there is partial truth in the comment about the cyclone geometry. Operating pressure, it indicates that it's quite important. And it indicates that higher pressures generally improves the separation efficiency, but it may increase energy consumption. Just be careful on this statement. Higher pressures impacts on the differentials around a dense medium cyclone. So it's not necessarily improving the separation efficiency, but we need to operate at the correct operating head based on the supplier guidance. Medium density, it indicates that that's important. And yes, we need to operate at the correct cut density. It indicates that adjusting the density can impact on the cut point and separation efficiency. I'm not so sure about the separation efficiency because the cut density or changing the medium density is predominantly influencing the cut point. It also indicates that the density can be controlled by adding or removing medium. And in actual operations, you're adding or removing water. Feed rate is indicated to be quite important, and I agree with that statement. Overloading the dense medium cyclone can reduce the performance because you're affecting the medium to ore ratio. But the statement of underloading the cyclone can lead to inefficient operation, I don't agree with. I haven't come that across. So there's a bit of a question mark around that last portion. Overflow and underflow settings. Adjusting the settings on the overflow and underflow outlets to achieve the desired product qualities. And it indicates here controlling the spigot and vortex finder diameter to control the quality. That is absolutely nonsense. We don't adjust the spigot and vortex finder on a dense medium cyclone. We do that on a hydro cyclone. We adjust the dimensions to accommodate for the yield changes within the washability. Then cyclone maintenance, it do indicate it's important to inspect the unit. And then it talks about inspecting the vortex finder and cones to prevent blockages and where that could affect the performance. I am in agreement with the where. However, the internals of the dense medium cyclone seldom blocks unless there is foreign material like wood or steel coming into the unit. So we inspect the cyclone predominantly not to remove blockages, but to check the wear profiles of the wear linings. So that is it on the general section. So the conclusion, selecting the dense medium cyclone is a process. That cyclone is then obviously exposed to certain conditions that will optimize its performance. But the cyclone is part of an overall process. So one also need to understand the factors that the process will have on the dense medium cyclone. So only focusing on the cyclone alone may result in situations which you cannot explain the strange behavior of the cyclone. So this unit that is empty inside and only has a vortex finder and spigot is often perceived to be quite simple. But the impact or the importance of its performance is often misunderstood or neglected. And that is maybe where people is, because of that misunderstandings, people don't pay attention to really what the contribution is of the dense medium cyclone. So the key to optimizing the dense medium cyclone is to focus on that what is not always obvious. So the empty vessel that we think is so simple, we've seen it can be quite complex because there are a lot of factors that's not always so obvious. I thank you.